And welcome to everyone. I'm going to allow another minute in case anyone's attending the presentation late, so if you can just bear with us for another minute, and then I'll start the presentation. Thank you. Okay, I'll start. Once again, thank you for attending this presentation delivered by Solfirm External Wall Installation Systems. Presentation title, Combustible Cladding, the Hidden Danger. As you can imagine, it's quite pertinent in the current circumstances within our industry, and I'll start. So, the contents, just an introduction to the presentation and Solfirm as a company, the history and background, pretty much an overview of events before, after Grenfell, a definition of what high-rise is, combustibility, defining exactly what combustibility is within building regulations, and fleshing that out for fire regulations, and then also delivering a segment on EWS1 cladding assessment forms and what they entail and how we can achieve compliance through that route. Non-compliance issues, Solfirm have been conducting many surveys on high-rise buildings, and we've come across quite a few non-compliance issues that we'll highlight, and then we'll also highlight the hidden dangers of cavities. If cavity systems that incorporate cavities for whatever reason, whether it be wind-driven rain, secondary defense systems, it's the hidden dangers that these cavities pose if they're not installed correctly. Another section on achieving compliance, how when attending a survey and establishing that there is a non-compliance issue, how then do we find a route to achieving compliance? And then finally, it's how we, Solfirm, can help. So just a brief overview on Solfirm. We're part of the Bollocks group of Berger Paints. Obviously, we didn't bring the Bollocks name over with our brand. It doesn't necessarily fit in too well into the English language, as you can imagine. We manufacture in Poland on a highly advanced production line that's ISO accredited. We have 30 years experience, and we're installing over Europe and the UK over 115 million meters squared of EWI annually. We're currently prevalent in 20 plus European nations and have a significant turnover, which allows us to invest quite heavily into research and development laboratories. Solfirm ourselves, as I've said, are part of the Bollocks group. We have BBA certifications, NSAI certifications for Ireland, and European technical approvals. We pride ourselves on our innovative solutions that generate eco uplifts for funding, and we're growing in the UK market, and this is due to our specification presence, and hence it's delivering sessions like this that's enabling us to do that. We have operating locations within the UK, those being in Milton Keynes, Glasgow, Northern Ireland, and Ireland. And we have recently invested quite heavily in an experienced sales team and technical team. Our mission statement, for want of a better word, is to inform and educate and advise. So we want to evolve the industry by developing innovative systems that deliver best practice. To do this, we need to invest in the expertise and people through technical and sales, with a vision to drive towards net zero solutions, taking climate emergency seriously. And we are very, very serious about fire, with providing our clients and customers compliance guaranteed systems to ensure that they adhere to building regulations. Innovation, as mentioned earlier, is also close to our hearts. We like developing innovative systems that, whether they generate additional funding or basically deliver best practice. This is something that we take pride in. So moving on to the history and background for this particular presentation. You can see there the picture on the left and the right is actually Grenfell before and after refurbishment. So Grenfell was built in 1974, a concrete frame, concrete panel solution, a compartmentalization fire strategy, 23 stories, 120 flats, 6 per floor, 200 bedrooms, and approximately 350 tenants. Now you can see with the rain screen cladding on the right, the refurbishment, which was complete in 2016, was a ventilated rain screen system utilising phenolic insulation and an aluminium composite material, or ACM. And the tenant capacity was there or thereabouts, very similar to before the install. So just to give you an idea, what is a rain screen? The purpose of a rain screen system is to provide thermal solutions, but also to manage wind-driven rain. They're also referred to as secondary defence systems. So the rain screen panel stops the initial penetration of the rain, and then there's a breather membrane that can manage any additional moisture that will get into the system, and that's classed as the secondary defence. It's ventilated to remove that moisture in between the panel and the insulation. Typically, it is phenolic insulation. Obviously, since the events of Grenfell, it's more moved over to mineral wool, and the rain screen cladding itself is typically affixed to a aluminium framing system or stainless steel, depending on budgets particularly. And you can see there the ACM cladding is one of the most popular. And you can just see horizontally and vertically there are intermittent fire barriers which manage the spread of flame within that cavity in the event of a fire, closing the cavity off. So background, we have a bit of a timeline just to demonstrate the speed of which this fire progressed up the facade. So you can see there at 0:54, the fire was reported to emergency services, and for the first firefighters reached the tower at 0:59. Now you can see the fire breaks out at flat 16 within 15 minutes of that call. And then within 33 minutes of the first call, the fire reaches the roof of a 23-story building. Now it came out of the 4th story, but that's still 19 stories of spread of flame. Flames then move across the building, the north and east elevations of the tower, and start to spread around the crown and diagonally across the face of the building, affecting flats in the southeast and northwest corners. Fire spreads horizontally across the south elevation at the crown, and flames continue to spread. And the diagram on the right just gives you an indication of the elongation of the flame within the cavity as it searches for oxygen, and the importance of the functionality of those intermittent fire strips to prevent that spread, which were obviously not effective in this particular instance. Potential contributing factors. Well, was the system installed in the exact same configuration that was tested? On the right, you can see a full-scale fire test, the BS8414. Typically, the system that's installed must be the exact system that is installed in real life on site. Now, in many instances, you may find that components have been substituted for either more economic components or just because of the availability. And that would mean that the test is not applicable and does not apply to that particular system. So was the ACM panel utilised of a suitable fire classification to BS 13501? These are just questions, not necessarily pointing the finger. Were the intermittent cavity fire barriers installed correctly, and were they tested in this scenario? A lot of intermittent cavity fire barriers, whilst are very effective, have been tested in scenarios that they're not actually being used, physically used on site. For instance, many cavity fire barriers have been approved for use between two masonry structures and within a cavity of 50 mil, for instance. and then they get used on rain screen cladding, which is not applicable to the masonry construction and may also have a cavity larger than what has been tested. And number 4, was the overall system installed in accordance with specification and reflective of what was tested, where products substituted with economic alternatives? Was the system installed in accordance with specification is an important point, because a lot of the time what we're finding when we're conducting the surveys is that the systems actually haven't been installed to specification for whatever reason. Now, the warnings were there. So in 1986, the Department of Environment warns about the use of combustible cladding. No change in regulation was made. A serious fire in 1991 took place in the tower block with rain screen cladding in height in Merseyside. You can see there in the bottom right-hand corner. In 1999, a fire at a PVC-clad tower block in Irvine, Scotland, in the top right. And in 2000, the Select Committee recommends that cladding products are entirely non-combustible, but ministers opt for large-scale firing testing. There are also other instances around the globe that were providing us with warnings. In 2014, the Lacrosse building in Melbourne. Believe it or not, the Marina Torch in Dubai caught fire 3 times, and the Address building in Dubai. There are others in China, Russia, and all over the globe. Also, then after Grenfell, there were a number of fires within the UK of a similar nature. You can see there a list in November 2017. I don't know, the Collie Moon House in Belfast, and in December 2017, the Lighthouse Apartments in Manchester and West Hampstead. So the problem is still here. So what happened after Grenfell? So on the 16th of June, this is just after the fire took place, which took place on the 14th, the government ordered social landlords to carry out audits on all the tower blocks. On the 19th, the government ordered social landlords to send those ACM panels for testing to laboratories. Of the 120 that were sent for testing, all failed. The government announces a program on the 6th of July of full-scale fire testing of ACMs only. 28th of July, a large-scale fire test using the exact materials as per Grenfell fails within 7 minutes. On the 1st of September, the government issues advice that field systems must seek professional advice, not necessarily outlining that specifically. And in October 2017, the National Fire Chiefs Council publishes guidance recommending walking watch fire patrols. Those of us that live in city centres will have witnessed these firsthand. 18th of December, Hackett issues her interim report, and on the 19th of December, 284 dangerous tower blocks were identified. Moving on to 2018, 10th of January, mortgage lenders start to refuse to lend due to combustible cladding, and this is a massive problem for the UK as it stands at the minute. Leaseholders start to be warned they face massive bills for the rectifications. By the 16th of May, the government announces that £400 million fund for the removal of dangerous cladding for the social sector only. On the 3rd of July 2018, leaseholders lose a tribunal, ordered to pay £3 million for the replacement of dangerous cladding. This is just laying the ground of what we're witnessing at the moment. So on the 3rd of October, the government bans combustible materials on high-rise buildings. And on the 28th of November, research estimates a further 1,600 buildings have dangerous cladding. 18th of December, the government publishes their advice note for external facades of high-rise buildings must be A2 or pass a full-scale fire test. Mortgage lenders start to refuse to lend en masse. So moving on to 2019, the government announced a further £200 million fund to address the removal of dangerous cladding, but this time from private sector And on June 2019, the government issued guidance for the removal of combustible materials in balconies. And one of those fires that I highlighted after Grenfell was a significant fire that involved balconies, and hence probably why that decision was made. 16th of November 2019, flat and apartment sales come to a complete standstill, estimating 600,000 people in unsellable properties. And this is where the EWS1 form is introduced on the 16th of December 2019 to declare buildings safe and allowing them to be sold and mortgaged. 11th of March 2020, the government announced a further £1 billion fund for the removal of all types of dangerous cladding in the private sector. So that gives us an idea of the actions that have taken place and brought us up to date currently. But for us to understand where the problem arises, we need to understand what defines a high-rise. Generally, it's a building which is higher than the maximum reach of the firefighting equipment, and any structure where the height can have a serious impact on evacuation. Now, these are just general terms, and we're going to go into the more specific geographical definitions of what high-rise are. But where the number of stories means the occupants need to use a lift or elevator to reach the destination, that can also be classified as a high-rise structure. The applicable fire regulations, well, in England and Wales, that's approved document B. In Scotland, it's Building Standards Technical Handbook, Regulation 2. Northern Ireland, it's Technical Booklet E. In Ireland, it's Technical Guidance Document B. All have slightly different views on what high-rise is. So in England and Wales, it's defined as a high-rise building as a building with a story at least 18 metres above ground level, not including rooftop plant areas. Now, the government's currently in consultation, and it's likely that this will reduce to 11 metres. So you can imagine that will open up a significant number of additional blocks that will have to have that EWS1 form. Scotland have already adopted the 11 metres. It's the same definition as England and Wales. It's just that it's 11 metres as opposed to 18, and it defines high-rise as a building with a story at least 11 metres, again excluding plant. Moving into Northern Ireland, this defines a high-rise building as a building with a story at least 18 metres above the lowest ground level. Again, just a slight adaptation on what we discussed earlier for Scotland and England and Wales, but still it can be quite pertinent if the ground levels are sloping, as is demonstrated in the graphic to the right. Again, not including rooftop plant areas. And for Ireland, it's quite a bit different. It defines a high-rise building as an 18-metre building. Ground level is measured as a mean, as is the roof level. So that is the most different from the ones we discussed. So to understand then combustibility, there are 4 tests that contribute to defining and understanding BS-EN 13501, which provides the classification for combustibility. You have a single burn item test, you have a single flame source test, you have a non-combustibility test, and you have heat of combustion test. All of these tests contribute to providing the classification as is disclosed in BS-EN 13501. Now, the main classification, and many will be familiar with it, is it can be A, B, C, D, E, all the way to F, or A1, which is the highest classification, which means totally non-combustible. But if you're not A1, you then typically get a smoke classification, which is associated with that. Now, it's indicated by either S1, S2, or S3, and S1 is being the best classification or the weakest emissions, smoke emissions, and that's really what we should be aiming for, because smoke kills just as much as fire, if not more. And flaming droplets, this is an important classification where I'm concerned, and again, very similar to that of the smoke classification. is either D0, D1, or D2. D0 is the best. Why it is important? If you're on a high-rise building which is surrounded by parked cars, for instance, if you have a high classification for flaming droplets, it's likely that those flaming droplets could possibly set fire to the surrounding cars or even an adjacent building. Therefore, what you're really aiming for here is a classification of D0. So this just gives further confirmation of what these classifications mean. A1 is non-combustible. A description is no contribution to fire. A2 is limited combustibility. It's very limited to contribution of fire. B, C, D, E, F, they're classed as combustible materials, but they change in severity, so it goes from limited to minor to medium to high to very easily flammable. So to give you an indication, E will be something like EPS, and D could be D and C are like phenolics. A1 is your rock wool. So smoke emissions, which we covered in the previous slide, S1, S2, S3. It's about the quantity and speed of emission of smoke. You can see S1 has a very weak emission, S2 average, S3 high. And the same applies to the D0, D1, D2 for flaming droplets. No dripping, low dripping, or high dripping. So if you are not achieving A1, and let's just say you're achieving an A2, you'd be looking to achieve a classification of A2, S1, D0. So we now move on to what is the EWS1 cladding assessment and how it works. And I've created a simple flow chart. Basically, when a high-rise building is suspected to have flammable cladding upon it, a fire engineer needs to do a desktop research on the specification and the cladding. And at that point, the fire engineer can actually deem the building sufficient with their expertise and knowledge of what's been installed, sufficient evidence, and they can issue an EWS1 from that. If insufficient evidence can be ascertained from a desktop analysis, then we move to stage 2, where a report is required, and that requires either a non-invasive inspection, a low-invasive inspection with keyhole, or a fully invasive inspection, and that will just depend on what is outstanding from the initial desktop assessment. For instance, the engineer may want to know what insulation is in the cavity, which isn't apparent from the outside of the building. The fire engineer then creates a report, and they then can issue an EWS1 report for no remediation at that point. But if they do deem that there are issues, then a remediation report will be prepared and tendered by contractors to rectify the situation. Whilst this is all going on, the other suspected elements that may be affected, i.e. internal elements, will also be inspected. The works are then complete to that remediation report, and then an EWS1 form is issued after final inspection by the engineer. So, as I mentioned right at the beginning of the presentation, we have come across a number of non-compliance issues when we're conducting these invasive surveys. One, fire barriers. They're either they can be installed incorrectly or just not installed at all. Cavity fire barriers, again, they're either installed incorrectly or not at all. Combustible insulation used where non-combustible should be specified and installed. It's non-compliant insulation installed at height or not tested effectively, like we were saying about the BS 8414 test. Systems installed not in accordance with what has been tested. Combustible sheathing boards is a big one as well. Every time that we're opening up lightweight steel frame constructions, what we're finding is that the actual cement particle boards or sheathing boards are combustible. And then doctored test reports for certain materials. I won't go in this too much due to legal reasons, but if anyone's up to speed with the news at the minute, there have been issues with certain material suppliers not providing testing reports applicable directly to their materials. So here we just have some photographs of some invasive surveys that we've done, and it's just highlighting some of the things that we've come across. So we've cut open a hole on the left-hand side, and in the middle you can see that there is a fire barrier. There's a mineral wool fire barrier, but there's a cavity behind the system. And then, so the intermittent fire strip should be installed correctly. In this instance, it's loose. So in the event of a fire, there is a possibility it could dislodge and not serve its purpose. So this makes it non-compliant. Cavity fire barriers, no intermittent fire barrier installed at all. So as you can see here, we have a ventilated render system onto a steel frame, and there's no intermittent fire barrier at all. So if there was a fire to take place that breaks out of the window, similar to that in Grenfell, it would pass up that cavity unrestricted and spread to the EPS above it. So that's non-compliant. Combustible shearing boards, which I mentioned before, they tend to be, we're finding a lot of Class B, where we should be using A2, A1 on high-rise. Now, these may have been compliant at the time of installation if tested in accordance with the full-scale fire test, but what we're finding is these boards weren't the ones that we used for the full-scale fire test, and therefore they're deemed non-compliant. Incorrect fire barriers, you can see here, this is a ventilated system or a rain screen system with terracotta tiles. Now this should maintain a fully ventilated system, and they've installed full cavity fire barriers which are closing the ventilation of the system. Now whilst this might not negatively affect the fire performance of the system, it could have a detriment effect on its ability to manage the moisture as a secondary defense system. Non-compliant. No fire barriers installed at all. One of the worst case scenarios, there wasn't even an attempt in this particular instance to install a fire barrier. Non-compliant. So, non-compliance issues associated with intermittent fire strips. These are, you can see on the graphic on the right-hand side, these intermittent fire strips, which are used extensively in ventilated systems and cavity cladding systems. They're designed to keep the cavity ventilated, but close the cavity in the event of a fire and stop that spread of flame in the cavity. Suppliers only test, when I say suppliers, I mean suppliers of the intermittent fire barriers, only test in certain substrate configurations. I did touch on this before. Typically, it could be in a timber frame situation to a certain grade timber, or in a steel frame situation to a certain type of sheathing board. What we're noticing a lot when we're exposing and getting into these ventilated systems is this isn't the case. The intermittent fire strips or cavity barriers are actually being used generically in whatever configuration that's suited at the time, which can obviously prove dangerous and hasn't necessarily been tested. Strips, different strips required for different cavity depths. We've noticed that obviously there's undulation in substrates when it's getting built, and those undulations can be anything between 50 mil to 100 in some instances. But the cavity barriers that we found in some instances have actually been still for a consistent cavity. So if that cavity is due to the undulation in the substrate, it's actually increased by up to 50 mil. They're still using a cavity fire barrier that's only suitable for a 25 mil cavity. So it will become null and void and not fit for purpose. Here is a video just demonstrating how fire reacts when it enters into a cavity. And you can see the diagram on the left, which is similar to that makeup we discussed before on the main screen system. And the fire is just pretty content in that as it is there until it's starved of oxygen. And then you can see how very quickly it elongates. And the importance of the speed of these intermittent fire barriers to close off these cavities is immense. And you can just see how quickly it happens. And you can imagine the intensity and heat that is being generated at the edge of that flame as it searches for the oxygen. You can see the fire intensifies. So here, just again demonstrating on the right-hand side, we have a cavity system. But if there is an opportunity, we can offer a system that doesn't incorporate cavities and could actually be 100% non-combustible. Here just demonstrates some of the fire tests that we've been involved in when products have been misspecified, and it just gives a demonstration how quickly things can go wrong. So in terms of a fire breaking out of an internal space, a window for instance, that takes place 2 to 3 minutes, and the flames do not cause damage in that 2 to 3 minutes on what is here being demonstrated as an EWI system with EPS. But within 4 to 5 minutes, the EPS is melted away and the fixings start to flex and melt. By 6 to 7 minutes, the flame enters the cavity behind the system, the render starts to spoil, gases start to expand and feed the fire, and it creates a significant hazard to life and escape. By 8 to 9 minutes, you can see there that the system experiences total failure and ultimate collapse. But we can't just consider fires breaking out from windows. We do need to take into consideration things like bin fires and garbage fires on the outside of buildings, car fires even in car parks that surround buildings of this nature. So how do we achieve compliance once we know that the system is combustible? Firstly, we can scenario one, which is a desktop analysis and the completion of an EWS1 by a fire professional. Scenario two is remedy. We can do a physical facade inspection, an introduction of fire barriers, and a replacement of combustible materials, a fire testing of panels, and then the completion of the EWS1. But in many instances, what's happening is scenario three, which is a full strip and reclad. So a physical facade inspection, you fully remove the existing system and sheathing, and you replace with a 100% compliant system, and then that ultimately leads to the completion of the EWS1 form. So how can we help? Initially, we can engage and assess and conduct assessments of the building. We can provide a fire engineer to professionally evaluate what is on the building, accommodate practical investigation via rope access if required, and implement remedial work, so supply certified systems, non-ventilated systems, installed by trained and registered contractors, where we adhere to a stringent high-rise and complex project policy, which I'll demonstrate in a minute, and also complete the EWS1 form. Provide 100% compliance guarantee after that process, and offer industry-leading warranties. The high-rise building policy is designed to manage the risk of our clients and tenants. It's 10 easy steps. We only use certified systems, whether that be BBA, BDA, or ETA. We only use systems that are A1 or A2 S1D0. We ensure we conduct a U value and condensation analysis within the requirements of building regulations. We only use European technically approved mechanical fixings. We implement robust detailing driven from our trade association, ensuring, because a lot of these buildings, it's hard to get to these details and maintain them, so they have to be robust and with as least maintenance as possible. A structural survey, we insist that the contractor / client conducts a structural survey on the substrate to ensure that it is capable of taking the dead loads that are associated with our system design. Number 7, we conduct pull-out tests in accordance with relevant recommendations. We do those on site, and when it comes to high rises, we conduct them on every floor as well. We conduct wind load calculations in accordance with approved document A, and that's in accordance with BS-EN 1991. And we only install with a small network of registered contractors that are approved for high-rise buildings. And contractors are also PAS 2030 and 2035 accredited, ensuring they are all fully familiar with the system specification and installation requirements. Site support, this is really important for me because having witnessed some of the installations just not being in accordance with the specification, it's very important that these site technicians are visiting site at least once a week, ensuring that the system's being installed to specification. So our solutions that we can offer to address the situation of combustible cladding, well, we have 6 main brands. We have a premium, which is an economic and fast and lightweight system. Now, this isn't a brand that we'd utilize for this particular problem because it utilizes EPS. The Ultimate brand, that's fire safe and reliable. Endurance brand, that provides industry-leading durability. Deco, eye-catching brand, it's more of the architectural solution, so brick effects, wood effect, etc. Solus, which is a render-only system, and Balance, which is dry-fix system. Again, these won't necessarily come into play when addressing the EWS1 requirements. But you can see here how our brands are all pulled together. Ultimate is probably the most suitable solution for addressing these issues. We can have a dash system there. You can see the accreditations, BBA, NSAI. It's A1 non-combustible. It's available in a number of colours, and it's also can be utilised on steel frame. We also then have our silicon HD system. Again, with all the approvals, it's A2S1D0, so it meets the requirements of building regulations and comes in various textures. And we also have a fully non-combustible system, A1 non-combustible, which is called Ultimate A1 Mineral. Again, it's has all the relevant accreditations. It's the only BBA certified A1 system in the world. There are other A1 systems out there, but they don't have BBA accreditation. This is an A1 EWI system. Fire regulation compliance is 100% guaranteed when utilizing this system in the event that you go down scenario 3, which is your strip and recard. Utilization of specialist A1 components and materials are what allow this system to achieve this industry-leading A1 fire classification. And it can be utilized with 300 plus different colours. The endurance system, this is extremely unique in the industry due to the high impact resistances that it can be achieved. The system itself, this particular system, which is Endurance WHD Silicon, can achieve 36 dual impact. That's 4 times better than category, the best in classification for EWI systems. So if you're down at low level, you want to increase the longevity, this is the system of choice. We then have the same system, but with an improved use of reinforcement mesh, providing an impact resistance 8 times better then best in classification. Again, both of these systems achieve the required fire classifications as well. And then we have our innovative solution, which can generate innovation uplifts, which is our Endurance 75 silicon system. This is a 75-year effective life system. We tested this through industry-leading accelerated age testing and statistical regression analysis. As you can imagine, it's very unique in the industry in terms of its durability and some of its other technologies. Deco, again, these are systems that can be used. Typically, these get used at low level to provide a decorative solution. And now we come on to why you'd actually choose Solfirm to assist you if you were to have a building that had been deemed to have combustible cladding. One, we conduct the U-value calculations, condensation analysis, and we can also conduct roofie calculations with our technical teams in Poland, which is unique in the industry. CAD drawings, a suite of standard details, although on high-rise buildings, as part of our policy, we provide a bespoke detailing pack. We conduct the wind load calculations in-house with our qualified engineers. This means a very quick turnaround, and we can get fixing patterns updated very quickly. As mentioned before, we utilise registered contractors, a national network of highly trained and experienced contractors. Site support, I won't go into it again, but you know how important I believe this to be. If it isn't monitored and assessed by our technical managers, it has the possibility not to adhere to specification in certain instances. Innovation as well. Well, Solfirm are a very innovative company with innovative systems, allowing clients to extract additional funding. We're funding experts. We can provide funding advice. We develop partnerships. We like working in partnerships with industry leaders, generating a deep understanding of government obligations. Our innovative systems, next generation systems, qualify for uplift. So that's an extra 20 to 25% in many instances, which is very significant on a number of projects. And that concludes the presentation. Thank you so much for your time. If anyone has any questions, my team, including my sales director and my design manager and my marketing manager, will do their best to answer them. Ruth, are you coming on microphone?
You've answered most of the questions. I'm just scrolling through, Mark.
Okay. I assume everyone who's attended will have all my contact details, so they can contact us if they have any further outstanding queries.
Mark, there's a question from Helen Clark. Do you just want to elaborate on the A1 system once it's painted?
Yeah, what's the exact? Okay, Helen Clark.
Once it's painted, how does this impact on the fire rating?
No, it's BBA approved and fire tested with the paint. It's a specially formulated paint that we've utilised, so the system still remains A1. We have the fire test certificate we have the fire test certificate which includes the paint, and we also have the BBA certificate which includes the paint confirming it's A1. So it will have a slightly lower organic content to allow it to do that.
About the warranties, how long are the ultimate systems guaranteed for and warranted?
Typically, we warrant the systems as standard for 10 years, but we do offer 20 to 25 years on funded projects. But on high rise, our typical offering, due to the complexity, is 25.
Rob Langley, also on the A1 system, it showed a masonry structure.
Yeah, it does show a masonry structure where we do have approval for the use onto steel frame. Direct fit.
And then another one from Helen. How long before it needs to be repainted?
Typically, it all depends on environment and location. It will be 10 years, every 10 years.
And I think that's it. I don't think I've missed anyone.
Okay, well, I guess we can conclude here. I'd like to thank everyone for their time today. I know we've all got busy agendas, but if anyone does have any further questions, then please feel free to ask those, and also download the handouts that are available on this platform. Thank you.
Thank you.